how additive manufacturing will help us make electric cars on this episode of the Cool Parts Show.
This episode of the Cool Parts Show is brought to you by Carpenter Additive.
We're at the company's powder production facility in Athens, Alabama.
Specifically, we are standing on top of the Z1, the company's largest vacuum atomizer for producing metal powders.
Want to know how to make metal powder for additive manufacturing? Stick around after the episode. I'm Pete.
I'm Stephanie.
Welcome to the Cool Parts Show.
This is our show all about cool, unique, interesting, amazing 3D printed parts. And Pete, what is this crazy looking thing we're going to talk about today?
So this looks intense, doesn't it? Let me tell you about this. This is the solution to a challenge in making electric cars. Machining is the answer to the challenge, but 3D printing is vital to the machining.
Okay, so be a little bit more specific. How does this big cylindrical spiky thing help me make an electric car?
The motor for an electric car, the housing of the motor, has this big hole in it, this big bore. It is the bore that holds the stationary part of the motor, the stator. It has to hold it precisely in the right position, and so that bore is machined precisely, and that's what this tool does. It precisely machines out that stator bore in a car's electric motor. But the thing is, this is automotive manufacturing, so you got to make a lot of these housings, machine a lot of these bores. You got to do it efficiently. How do you machine it? So that big bore, that big hole in the part, one way is a lightweight tool, maybe like in a helix shape, like to make that big hole. Not very fast. Another alternative, like one really big honking tool, just like shoom, and just machine the whole thing out in one pass. Problem there, that tool is liable to be super heavy, likely too heavy at that size for the machine tools that are doing this work to be able to wield a tool like that effectively. So the question is, can you make a tool that is both big and lightweight? Enter additive manufacturing.
Okay, so I'm with you so far. Electric vehicles need these large stator bores. The fastest way there is to use a very large cutting tool, but building a tool this large conventionally might mean that it is too heavy for the machine tool to use, and so here 3D printing is providing the lightweighting, right? Except this tool does not feel lightweight at all.
So yeah, lightweighting is relative, isn't it? For reference, a tool this size, made conventionally, a comparable tool made without additive manufacturing probably weighs twice what this tool does, 2 times. And a tool that heavy, so the machine tool in question, it probably wouldn't be able to swing a heavy tool like that around in its tool changer and load it up into the spindle, and the weight might deflect and might work against the tolerances you're trying to hold because of all of that mass. Yeah, this is still kind of heavy when you try to pick it up, but it's super light for a tool this big, and that's what additive manufacturing brings. That like cutting the weight in half at least results in a tool that is light enough for the machine tools to use, make use of effectively to efficiently machine these big, precise holes.
Okay, very cool, and I want to hear more about that. But let's talk 3D printing. Who made this and how?
This tool was made by Kennametal, well-established cutting tool maker, and Kennametal has an additive manufacturing group. And Kennametal is starting to take that additive manufacturing knowledge and apply it to cutting tool manufacturing. And the company has standard products now, off-the-shelf catalog products that are manufactured through 3D printing, but these are smaller tools. They're very small tools. This is an extreme case of additive manufacturing to make a cutting tool. Very big tool, does a lot. We actually have 2 versions of this lightweight tool, including one that's even a little lighter than this one. I'll get to that. But this version, you can kind of see 3 metal 3D printed sections that were assembled together. additive manufacturing doesn't account for all of the components or all the functionality. These cutting edges, cutting inserts are made of a very hard material, good for cutting metal, made in a separate process. For more about this tool and how it's made, let me introduce you to someone. This is Werner Penkert. He is manager for advanced machining and additive solutions for Kennametal.
We use laser, powder bed fusion, 3D printing processes to manufacture the steel components of this tool, which enables us to reduce the weight and incorporate complex geometries that would have been difficult or impossible with traditional manufacturing techniques. After creating the body of this tool, we use milling, drilling, EDM machining processes to create the pocket seat of the PCD, the polycrystalline diamond reaming inserts. We also epoxy PCD guide pads and grind them for precision. Overall leverage of the 3D printing technology resulted in the part required significantly less machining, has a much lower weight, and allows more complex geometries than traditional manufactured tools would have.
Okay, so we sort of started this conversation by talking about lightweighting, and I can sort of see like some of the choices they made to reduce the material used to get the weight down. But from what Werner's just said, I'm gathering that there's a little bit more going on. Like, what are the other design opportunities that they realized through 3D printing?
So we've covered 3D printed cutting tools before. Do you remember that episode? And so it was a 3D printed end mill, and part of the reason for 3D printing in that case was to get coolant through the tool, get the cooling fluid to flow through the body of the tool with channels 3D printed in to sort of channel that cutting fluid exactly where you want it to go. Okay, so that's going on here too, and again, it's more extreme in this tool. So built-in coolant passages all through this tool, flowing through the body of this tool, so that coolant exits everywhere these cutting edges need it, all around the tool, all around these cutting edges. And the coolant not only helps with the cutting, it helps with something else too. This tool's machining is so precise that in order to guard against the tool rubbing against the inside of the bore as it cuts, the pressure of the coolant going through this tool and kind of spraying out in all directions at once, it guides the tool. The coolant itself acts as a hydrostatic bearing, and it's part of the functionality of how this cutter precisely cuts.
Okay, so the 3D printing is actually doing a lot here. It's helping to provide the lightweight. It's allowing for those coolant channels that are actually guiding the tool, and the tool itself is doing a lot. It's cutting that big hole in just one pass.
Can I jump in there? Because I've actually kind of undersold all that this tool does. There's even more going on than just machining one straight hole in one pass. It's actually machining a variety of different features. So this front part here, it machines the bearing surface, the place where the bearing for the rotor mounts, the rotor, the part of the motor that spins inside of the stator. Very precise. Then this part, this sort of like array of cutting edges, that's what machines that long central bore, the stator bore. And then this part at the back, it's actually cutting at a diameter that's a little larger than this first section. And that larger diameter, it creates sort of the recessed surface where a cover plate goes in. All of that has to be machined at very tight precision. And in fact, this bearing mounting section in particular, it has to be on center line with the rest of this larger bore so precisely, like the margin for error is something like 20 microns. And so having this one big solid tool, it allows for accuracy and efficiency all at the same time. All of these different features are machined in that one pass.
So this is not just one 3D printing cutting tool. This is like 3 cutting tools all together doing 3 different things all at the same time.
So yeah, at the very least, this one tool performs a series of operations and it replaces at least 3 different tools.
Okay, so where are they at with this? Is this a tool that's actually being used in automotive production right now?
Yes, a different version of this is. So let me show you like the next iteration of this design. Like it's a little lighter weight. It's a little lighter weight, and you can see the difference here. You can see the difference. So the simplest 3D printed section, which is this sort of central shaft. In this next iteration, it was replaced with carbon fiber composite. And so this is cutting tool maker Kennametal basically using all the different options and technologies they have available to try to get the lightest weight, best performing tool they can. So these cutting sections still made through additive manufacturing and looking for a little more weight savings using carbon fiber composite.
So both versions of the tool provide a significant advantage in terms of weight. Our all steel version is 10.7 kilogram, which equals 23.5 pounds. Our steel CFRP steel version has a weight of 9.5 kilograms, which equals 21 pounds. Compared to the conventional aluminum or steel tool bodies, that represents about 40 to 50% weight reduction. That matters because spindle interfaces are limited with weight and momentum of inertia.
So you asked, has this been adopted? And the answer is yes. So these tools are demonstrator models. This is Kennametal's engineering team demonstrating, proving out that a tool like this is a powerful, effective solution for manufacturing electric vehicles, electric motors. And yeah, there is one automaker who is convinced this is the effective way to go, and they've the tool has continued to develop. That automaker, along with Kennametal, has refined this design and sort of taken it to the next level, improved it even more. But essentially, yeah, this tool is now used in serial production day after day, producing electric motors for EVs.
Our mission is all about improving performance for our customers. We want to help them to cut faster, run longer, and machine with greater precision and process security. We see the 3D printing as a key innovation enabling technology because it offers huge opportunity to improve performance and deliver value to our customers. Enables lightweighting with strength, production of complex part not possible with traditional methods, optimize the design and the performance. The demonstrator tools generated interest from a number of customers, from automotive industry, their tier 1, tier 2, and their broad subcontractor base. We are currently implementing an enhanced version of the steel CFRP steel version into the production of a serial production of an automotive OEM customer.
Okay, I think I got this. So these are two different versions of a cutting tool made with 3D printing. They are designed to cut the main stator bore in an electric vehicle motor housing. But actually they're doing a little bit more than that. They're cutting the main bore, but they're also cutting the bearing seat and the housing cover seat. So it's really like three different tools in one. Creating a cutting tool this large allows you to cut all those three things in just one pass, which saves you a lot of time. But building a tool like this conventionally would mean that it's probably too heavy for your machine tool to handle, and that might influence the kind of cutting results that you get. So Kennametal, which is an established cutting tool company, took a stab at creating a new type of cutting tool. They developed this design first, looking to save weight, and they reduced the weight by about half versus a conventional version. But moving to laser powder bed fusion also allowed them to include these internal cooling channels to help this tool be even more efficient and functional. Looking for additional weight savings, they then went to this design, which incorporates a carbon fiber body in place of the 3D printed piece. And a version of these tools is actually currently being used in the production of electric vehicles.
Thanks for watching. This is actually the second time we've gotten to talk about 3D printing for tools for machining. We'll put a link to the earlier episode about a 3D printed cutting tool in the show's description. Find all of our previous episodes at thecoolpartsshow.com.
If you like the show, we hope you'll subscribe, leave us a like, leave us a comment, and if you have a cool 3D printed tool or other part, you can email us at coolparts@additivemanufacturing.media. Thanks for watching.
This episode's brought to you by Carpenter Additive. We are at the company's powder production facility in Athens, Alabama, and we are standing on top of an atomizer. The Z1 is Carpenter Technology's largest vacuum atomizer, and it is the heart of the process for making additive manufacturing metal powder here at Carpenter Additive.
This facility is capable of producing up to 18,000 pounds of metal powder per day. Plant manager Jordan Ralph talked us through the process.
So an atomizer is a piece of equipment that is capable of melting and pouring molten metal into the stream of high pressure gas that turns that molten metal into tiny, tiny droplets that ultimately cool and form our powder, which looks like gray dust. So to start our process and the ultimate end-to-end solution that we have here, we bring in raw materials all the way down to individual elements, so nickel, cobalt, chrome, moly, niobium. We bring all of those raw materials into the shop. We utilize those materials to build charges that go into the atomizer. As you walk that flow path, you run through our charge makeup area where all of the materials are weighed out in very exact quantities. That ensures that we're able to hit our customer specifications and hold the tight tolerances that we're looking for on a chemistry perspective. From there, the material is flown to the top of the atomizer and charged into the furnace. As the material is produced, it's poured out and is collected at the bottom of the atomizer. The material is then taken and transferred into a bulk container for processing through the rest of the value stream. The next stop for any of our atomized powder would be the screener. So that will remove the coarse portion of the powder. From there, we take it through air classification. That takes the fine portion of the particle size distribution out and makes the final cut for an additive material, like a 10 to 45. From there, we stack up all of those individual lots and put them into the 12,000 pound blender to make the single homogeneous blends. At that point, we are able to pack in any configuration that the customer is looking for, whether that be drums, bottles, powder trace hoppers. Really, we've got a lot of options to meet customers' needs there. The atomization capability and all of the powder capabilities gives us a unique position where we're actually able to produce the powder, run testing through additive machines all the way through HIP and heat treat, do final testing on those products, and then make additional changes or try to optimize things like our chemistry or sizing so that we ultimately can serve our customers better.